Okay, now let's get deeper into principal component analysis. Let's assume that we have two features that we have collected from people. Let's say it is height and weight. All right? And let's say that we have around 6 samples from 1 all the way to 6. And they are filled in a certain way. Now, how does PCA actually work? Graphically, we can draw up to 3 features, but the math can do any number of features, doesn't matter. So whatever we're going to learn here can be generalized to any number of dimensions. Even though we cannot draw it, the math can still hold and can be applied without illustrating it. So let's start here. I'm gonna be drawing my data. Let's assume that we have 4 points instead of 6, all right, so that we can easily draw them. Let's say that we have point here, 1 point here, 1 point here, and let's say 1 point here. Let's say that this is the weight and this is the height, doesn't really matter. And these numbers does not really reflect here accurately, but we just wanna clarify things. All right, so the first thing you do is that you actually project these into the h-axis or the height axis and the weight axis. So if we project them like this is what would happen. All right. Now what we need to do is to actually calculate the average of these points on the w-axis. We projected them, right? What do I mean by projecting them? It's like, think about it like you have put these dots and they are now on the w-axis directly, okay? So this is what projection means. Now if we take the average here, after they are projected, the average value, let's say that it is located right here. We will do the same thing and we will project all of this data on the h-axis like that, and then we will calculate the average again. Let's say that the average of this point is actually around here, and now we need to connect these two averages together to get a new point. Let's say that the new connected point is, after we have connected the two averages, is actually around, let's say here, okay? Now, we are going to do some shifting. We are going to choose those 4 points, the red ones, and the white point, and move them to the origin. Right? So this white point needs to be at the origin, and the spaces between the red points and the white point, which is the center, need to stay the same. So it's like cropping this section and just putting it on the center. Let us do that quickly. This is my center. Those are my points. Okay, so as you can see, the shape of these points is still the same. We just shifted them from this place all the way to this place. This is what we've done. All right. Now, what's the next step? We need to find the best fitting line. How do we find the best fitting line in here? Well, we need a line that fits this data the best, okay? How do we do that? Well, let's say that this is the line here we are starting with. Okay, what we need to do is we are going to project those points on that line. Say here, say, so we projected this, we need to project this as well. Let's say here, and then we need to project this one, and we need to project this one, okay? And now what we are going to calculate is the distance of every point to the origin. So this is the projected point, we need to calculate its distance to the origin. So from here to here for the first point. Now the second point is going to be from here to here, right? From the blue one to the white one, okay? Now let's say for this blue dot, we need to calculate the distance from here to here. And we are going to write them. So let's say this is distance 1. We are going to say distance 1, okay? And then after distance 1, we need to say this is distance 2, this point is distance 3, and this point is distance 4, okay? I hope you are seeing what I mean here. So we just sum up all of those distances together. All right? Now let's say that we got a number of, I don't know, 12. All right? Doesn't really matter. Now we are going to repeat this multiple times. So let's memorize that the first distance is 12. I'm gonna just erase that. Now we are going to try a different line. Let's say that the line now looks like this. We need to project all of these data points. So this is data point 1. We calculate the distance to the origin. And then this is data point 2 we projected. And then we calculate the distance to here. Then we have data 3, etc. And we need to calculate this small line. And that's it. And then we record all of those. All right? Now we call every distance that we have calculated the sum of squared. Okay, so let's say sum squared for the first line is 12, sum squared of the second line is 20, etc. And we take the highest one, okay, and that would be our line, the one with the highest distance. Let's say that our line looks something like this. Okay, this is the line that maximizes the distance. Now we call this line actually the PCA1 line. All right, and now we get the slope of this one, the slope of this line. Now what this slope tells us that if we move, let's say 3 units here, we will be moving only 1 unit here. Right? This means that a change on W of 3 units is yielding a change of 1 unit on H. So W is really important because it's yielding a lot of variation here. Now, if I draw this line right here, this is what we call the eigenvector. You will hear the term eigenvector whenever you are working with PCA. And this is it. It is actually a measurement of the variation here. And as you can see, this is how we just extract it from these two vectors that we have calculated after we draw the PCA1 line. So whenever you hear eigenvectors, now you know what they are talking about. Now the next step after we done that on the PCA1, we would like to project everything, but this time on PCA2. Well, PCA2 is actually a very simple line. We can draw it just perpendicular to the PCA1 line. So we can simply just draw a perpendicular line here, and this will be my PCA2. So this is PCA2. Why is PCA2 important? Well, I'm just gonna draw another graph because this is getting crowdy. Now take a look. This is my PCA2, and this is my PCA1, perpendicular to it. All right, and those are my points. We have a point here, we have a point around here, we have a point around here, and we have a point around here. Now, what we need to do is to project those points on PCA1 and PCA2. Let's make the PCA1 projection. So the first point, this one is going to be projected here. This point will be projected here. This one will be projected here. And this one will be projected here. Okay? Now we will go again on this point. This will be projected here. This will be projected here. This will be projected here. And the last one will be projected here. Okay? And just by the way, before I forget, the vector here is called the eigenvector for PCA2. The same way we have created an eigenvector for PCA1, this is the eigenvector for PCA2. Okay, let's continue here. Now it's time to rotate back everything. So this is my PCA1 right now, and this is my PCA2. All right, we have rotated it back. And those are my points. They are still there. Let's say that we had point 1 here, 1 here, 2 here. And let's say that we have 2 points here, like that, and 2 points here. Now all we need to do is to actually connect the samples together. Because every sample we have projected it on the first PCA axis and the second PCA axis, we can just reconnect them together. So let's say this is point 1, let's say this is point 2, Let's say this is 0.3 and let's say this is 0.4. As you can see now, we got clustered data. Can you see that? We had data that are just plotted according to the features, and we ended up with clustered data that are separated from each other. Now, all of these mathematical terms that I said, eigenvectors, calculations, projection, all of that is actually a whole mathematical formulas that you need to apply in order to get these results, and they can be applied to any dimension. I try to visualize it to you so that you can understand what's going on under the hood. But in reality, all of that is done just using pure math. So if you go back to pure math, you can see that you can apply this to any number of features, doesn't really matter. Now, these eigenvectors are mentioned many times, but what are they? I mean, why am I giving them such importance? See these arrows that I've drawn here and here, and I told you this is the eigenvector for PCA2 and PCA1? Well, it is the same value as the squared distance that we have created. Remember this highest value? Well, this is actually the same thing as saying that this is the eigenvalue. And why it's important? Because it is showing me variation. Okay, so this is my eigenvalue 1. How is it showing me variation? Well, if I just say square distance PCA1 divided by the number of samples minus 1, I would get the variation of PCA1. I'm going to show you in a minute why it's important to get this variation. Now, if I take the same thing for PCA2, and I divide it also by n minus 1, we get the variation of PCA2. Now, just for the sake of example, I'm going to say that PCA1 is equaling to 12 and PCA2 is equaling maybe to 4. You'll see that the variation for PCA1 is higher. It means that PCA1 is more important than PCA2 because it has more variation. What do I mean by variation? It means that the data is spreading out on the PCA1 axis more. If you remember when we talked the last time, I told you that the PCA1 measures how different data is from each other. And the more the variation, the better, meaning that we are having more distance. It means that we are having better clustering. So most of the information is actually condensed in PCA1 on the PCA1 axis, and less information is condensed in PCA2 axis. This is why we have a plot that we usually plot for PCA, which is called a scree plot. Now, what is a scree plot? A scree plot is going to be like the following. It draws here PCA1 and PCA2, and then here you have the variation percentage. All right? So how do we calculate the percentage? We just need to calculate the total PCAs and divide each one of them. So here we have 12 divided by 16 because it's 12 plus 4. And here we have 4 divided by 16. For PCA1, we got a result of 75%. And for PCA2, we got a result of 25%. All right? And as you can see, the variation on PCA1 is way higher. This is why eigenvectors are very important because, well, they tell you that where is the most variation is being held in which PCA. Now, PCA is usually equal to the number of features that you have. Okay, so let's say that we are drawing on 20 features. Most of the time, and in a lot of the time, in well-separated data, we will see that PCA3 is less, PCA4 is even less, PCA5 is even less, most of the time. So we see that it's enough to plot only PCA1 and PCA2. This is why PCA is great for representing in 2 dimensions, because most of the information after calculation will be collected in only 2 axes.